In this screencast, we're going to look at gradients, or the potential of a vector field, and the gradient of a function. We're going to start with gradients, and the idea is if you start with a function, f of xy, which is something, I'll just go x squared plus 4xy plus 3y squared. Well, we already know how to take the derivative. The derivative is a matrix. We take the derivative with respect to x, which is 2x plus 4y. And now we take the derivative with respect to y, which is 4x plus 6y. That is called the derivative, or the total derivative. Well, the gradient of a function, written with an upside-down triangle, or del f, is the exact same thing as the derivative, except rather than writing it as a matrix, we're going to write it as a vector. 2x plus 4y, comma 4x plus 6y. Now notice the gradient is a function which has two numbers coming in and two numbers coming out, which means it's a vector field. So the derivative is really a vector field. And anytime we take derivatives, we're really finding vector fields, which means we could find work, we could find all the other things we've been doing in this unit with vector fields. So what we're going to do now is we're going to suppose we didn't know the function. And suppose we only had a vector field that was 2x plus 4y, 4x plus 6y. And we didn't know this function we begin with. Can we recover f? If we can, then this little f is called a potential for the vector field f. If you start with a vector field and you can find a function whose derivative equals the vector field, that's called a potential for the vector field. So does the gradient of little f equal big F? In which case, a potential is the thing called f. It's related to potential energy, and we'll get there soon. So the idea, well, this came about by computing f sub x, and this came about by computing f sub y. So let's try and integrate this first function with respect to x, and let's integrate this function with respect to y and see what we get. If I integrate this with respect to x, I get a 2x squared over 2 plus 4xy plus some constant which could depend on y. I'm going to draw a bar just to remind me that I'm now doing a different problem. Here, if I integrate with respect to y, I get a 4xy plus 6y squared over 2 plus some constant which could depend on x. Because notice here when I took derivatives, anything that just had an x in it disappeared. Now I come and ask, all right, this should be the potential, this should be the potential, this should be the same. Are they? Well, this part right here only depends on x. Does it show up over here? It does right there. So the x squared, I can cancel those 2's, this x squared is really this constant with respect to x. The 4xy, does it show up over here? It's got an x and a y in it, which means that it better show up over here. It does. Are there any constants that only depend on y over here? Yep, we've got a 3y squared. So what that means is if I want to find the potential, the idea is, well, let's just write down the terms as we go. We got an x squared. We've got a 4xy, which showed up over here, so don't write it twice. And then the constant which depends on y is 3y squared. Now, if I hadn't even paid attention to the constants, I could have just said, it's an x squared, a 4xy, which shows up over here, don't include it, and the 3y squared. This is our function, and notice it matches what we started with. So can we recover functions if we have a vector field? And the answer, yes. Integrate, sum up the thing, but ignore duplicate terms. Let's look at one bigger example. We'll take 2x plus 3y plus 4z. I'm going to increase dimensions. 3x plus 4y plus 5z, and 4x plus 5y plus 6z. Does this have a potential? We're going to find it. So I first integrate this part with respect to x, I integrate this part with respect to y, and I integrate this part with respect to z. Well, integrating here with respect to x gets me to x squared plus 3xy plus 4xz. That completes integrating with respect to x. Now I'll integrate with respect to y. I get a 3xy plus 2y squared, I divided by 2, plus 5yz. Now I need to integrate this with respect to z, which gives me a 4xz plus 5yz plus 3z squared. Again, I divided by 2. Okay, this only has x's in it, which means I only need to write it. This has an x and a y, which means it had better appear here too. It does. Only write it once. 3xy. This has an x and a z, which means it had better appear here. It does. We'll write it. And now we've taken care of it in both spots. That term we already took care of. This term only has a y in it, so it should only appear in the middle. The 5yz shows up here. It also should show up here because it's got a z in it, so we'll ignore it. And then the last term is 3z squared. What we've done is we've shown all you have to do is sum up the terms ignoring duplicates, and that gives me a function. Is this function, is it a potential for that vector field? There's a simple way to check. If you want to check, all you have to do is compute the gradient of that function. So if I compute the gradient of the function, it's just precisely 2x, I'm taking derivative with respect to x, plus 3y, plus 4z, 0, 0, 0. Now I take the derivative with respect to y, 0, 3x, plus, and with respect to y, we got a 4y plus 5z, 0. Now the derivative with respect to z, 0, 0, 4x, plus 0, 5y, plus 6z. Are those the same? Yes. That means little f is a potential for the big vector field, the big F, which is our vector field. That completes the screencast.